Video is going to be on 3.5 and it's on applications. And what this is going to do is it's going to mix exponents and logarithms. And so I just want to go over the theory in this video, then we'll do practice video. So the key is we're going to look at exponential functions. And if you remember, an exponential function, I'm sure you remember, is of the form y equal b a to the t. And that's going to be the starting value. And that's going to be the base. Okay. So there's two things. We have exponential growth. If a is greater than 1, and the graph will look like this. It'll grow. So it'll be that familiar exponential curve. It'll go up like that. Okay. And what we're going to, so some examples of this might be investments. Population is another example. And another example might be in the growth, the spread of an infection. In particular, the R factor. And we started off with an example about that and also one about investments. Okay. Then we also have exponential decay. And that's when that base is less than 1. So it's still the same function, but this time a is less than 1, and the graph looks like this. It goes down. So it's the opposite of exponential growth. So it's exponential decay. And we're going to, again, that's going to be the starting value. And some examples of this might be something like population decrease. We'll see an example of that. So if a town or some area is losing population over time. Also, when a disease is starting to slow down, it will be the sort of the decay or the decrease of infections. That's another example that we'll go through. And I'm not going to go through this one, but you might see something like the half-life of a medicine or a drug. That would be another example. Okay, so the last thing I'm going to talk about in the theory is how we typically measure growth and decay. So how to measure growth and decay. So you remember that when you have exponential growth, a is greater than 1, so that means things are going to increase. So you want to find out when something doubles. So it's called the doubling time. Could be the doubling of an investment, a population, the spread of a disease, but it's one way to sort of measure the long-term effects. So you can compare one growth rate to another. And the formula is really just going to be, all you're going to need to do is solve a to the t equals 2, and I'll show you why. This is what the equation starts with. We want to find out when b is the starting value, so we want to find out when it doubles. So then what we're going to do is divide both sides by b. That's going to cancel out the b there. And over here, so what we're going to end up with is a to the t equals 2, doubling time. Since it's doubling, I wanted to write it twice. Okay, and if a is less than 1, you're going to talk about half-life. And that's how long something takes to cut in half. And we're going to end up solving a to the t equals, sorry, I want to make that clear that that's an exponent. A to the t equals 1/2. Okay. And again, the reason is going to be very similar. To find out when something decreases by 50%, we're going to solve b a to the t equals b over 2. So that's what we want to solve. And so we get b a to the t equals b over 2. Divide both sides by b like we did before. Those b's are going to cancel. Those b's are going to cancel. And we're left with a to the t equals 1/2. So I just kind of want to point out that those are the big equations. For half-life, again, things are cut in half. That's doubling time. This equation right here. Okay, that's it for the theory today. The next video will be some practice problems.